Okay, part two of our talk about the comparison test is going to be the limit comparison test. And as far as I'm concerned, this is the easier one to do. Now, you do have to kind of have some special circumstances to do this one, um, but it's much easier to actually do the limit comparison test, and hopefully the concept will make sense. So, the idea is this. If we have, again, we're going to be given some kind of a series, and we want to compare it to something. If we know that the other series that we're comparing it to, this is with the limit test, is either convergent or divergent, then if we take the limit comparison test and we know that the one that we're comparing it to is convergent, they're both going to be convergent if we get a limit. And if we get a limit and the first one is divergent, then they're both going to be divergent. So let me kind of explain how and why that works. So the limit comparison test, first of all, says that we're going to take the limit of the ratio of the two series. So what that's saying is if I take, and again, I use the word ratio on purpose, if I take the ratio of the two series here, that means what I'm doing is I'm taking the division of the two. Well, if I divide two series, if I take the limit of these two things which are being divided and I actually get a limit, it's very much like saying, okay, I'm taking the ratio, which is like a geometric series, and I am getting some kind of a finite value out of this thing. So again, let's kind of take a look at see what I mean by this. What we do have to know is that both series have to be positive in order for this to work. If we take the limit, and it doesn't matter whether this is a sub n over b sub n or b sub n over a sub n, that doesn't really matter, but we get an actual limit as n approaches infinity, then whatever one of them is, the other one will be the same thing. And the reason for that is because if we actually get a limit out of this, what that means is that the growth rate of these two series is approximately the same as n approaches infinity. And if that's the case, if we know one's convergent because the other one has the same growth rate, they're both convergent. If we know one's divergent because they have the same growth rate, the other one is divergent. The easiest and most simple way to put this is the best way to use the limit comparison test is going to be mostly when you have something which it resembles a polynomial, or let's not say polynomial because polynomials have to be whole number exponents, but it could be like a power function. So that's why we use p-series a lot in this case, because p-series look like rational functions, and that's exactly what we would be looking at, something similar to that. So again, the idea is if you compare the limit and you get some kind of a positive real number out of this, then either both series converge or diverge depending on what you compared it to. If the limit equals 0 or doesn't exist, or gives you a negative value somehow, which really shouldn't happen if you have two positive series, but if the limit equals 0 or doesn't exist, then the limit comparison test is inconclusive. We have to try something else. So this is important. If you get 0, which of course is a finite value, but it's not positive, or if the limit doesn't exist, it's inconclusive. Try a different series test. All right, so let's go ahead and look. Here's recalling your p-series. Remember that if p is greater than 1, the series is convergent. If p is between 0 and 1, the series is divergent in that form. You will need to remember that. So again, the limit comparison test works well for comparing messy algebraic series with a p-series, especially if they're, like I said, if polynomial or power functions, something like that, something where you've got the variables being raised to some power. All these examples are perfect examples of that. You can take a look at those. We're going to skip over that for now. All right, so let's take a look at number 1. Determine the convergence or divergence of this series. Excuse me. So what we're looking at is something which has the square root of n over n squared plus 1. What we want to do, in this case it doesn't matter whether you think this is convergent or divergent, you want to compare the top power on the bottom, the dominant term on the top and the dominant term in the denominator, which in this case is a n to the 1/2 over n squared. Those are the dominant terms. So this is our a sub n. We're going to call b sub n what we're going to compare this to, We're going to call that the sum of n to the 1/2 over n squared, which of course we can simplify because these two things are common bases. We subtract the exponents, and what we get is the sum of, let's see, what's going to be n to the 3/2 in the denominator, so 1 over n to the 3/2. And we know this series is a p series. P is 3/2, which is greater than 1, and therefore we know b sub n is convergent. Okay, so now what we're going to do, because we know b sub n is convergent, when we take the limit comparison test, we're going to compare this series with this series by doing the ratio and doing the limit of those, and if we get a finite value other than 0, then we know that a sub n is also convergent. If we get 0, or if we get does not exist in some fashion, or infinity, then we know that we have to try something different. So we're going to take the limit as n approaches infinity of a sub n over b sub n. A sub n, of course, is the original series, this one right here, so that's going to be the square root of n over n squared plus 1. B sub n is 1 over n to the 3/2. This is really bad notation, by the way. This is an AP test. They would give me a linkage error because I forgot to write my limit. So equals the limit of this. All right, well, this is a really difficult way to try and figure out this limit. You don't want to try and plug infinities into all these things right here. You want to simplify first. So we'll take the limit as n approaches infinity. That is an m there. So it's going to be square root of n over n squared plus 1 times the reciprocal of this, which is n to the 3/2 over 1. Which is the limit as n approaches infinity. Multiplying this top together, it's n to the 3/2 times n to the 1/2. Adding the exponents with common bases gives you n squared. So I get n squared over n squared plus 1. And this thing, because the powers are now the same, has a limit of 1. This is a finite value. Therefore, a sub n is also convergent. All right. Determine the convergence or divergence of this rational function right here. So what you should see is that the dominant terms on the top is this n squared term. The dominant term on the bottom is this n cubed term. So our b sub n is going to be 5n squared over 7n cubed. The sum is n equals 1 to infinity. And again, this is a sub n up here. Well, you should be able to see pretty quickly that this n squared is going to cancel out 2 of these n's in the bottom, and what we're going to be left with is the sum as n equals 1 to infinity of 5 over 7n. The 5 over 7 is a constant. That can be pulled out to the front, so we really don't have to use that. But this, you can tell, is 5/7 times the sum 1 over n. This is 1 over n. This is the harmonic p series, where p is 1. And the harmonic p series is divergent. So if we now take the limit of the ratio of these two things right here, what we should see is that if we get a finite value, that both series will be divergent. So let's try it. limit as n approaches infinity. Now I'm going to start taking a little bit more shortcuts here. Instead of dividing this one by this one, I know I'm going to take this one right here and I'm going to multiply it by the reciprocal of this one, because that's what division of these fractions is. So this will be 5n squared plus 9 over 7n cubed minus 2n plus 8 times the reciprocal of this one is 7n over 5. Now hopefully what you can see is that if I multiply 7n times this numerator, I'm going to get 35n cubed. That's my dominant term. On the bottom here I get 7n cubed. That's my dominant term. So as I take the limit, since they're both going to be cubes, I'm looking at the leading coefficients, which is going to be 35 over 7. And of course that simplifies to 5. Seems like I made a mistake somewhere. What is my mistake? Five n squared over 7n cubed simplifies to 5 over 7n. The 5 over 7 can be pulled out to the front, but it doesn't have to be, so I could leave it there. Oh, I forgot to multiply the 5 through here. Right, so really what that's going to give us is 1. Yeah, because if I multiply the 5 through here, I'd get 35 on the bottom, I'd get 35 up on the top. Those are going to cancel out to 1 once I multiply the n. Yeah, okay. So this, because I got a finite value, means that a sub n is divergent. There we go. So again, I think the concept is a little bit more challenging on this one, but as long as you understand that what we're doing is really we're just comparing two things almost in a geometric form by doing the ratio, then hopefully you can see what's happening here. If one grows at a rate that converges, since they're basically growing at the same rate, they both converge. If one grows at a rate that diverges, since they're basically growing at the same rate, the other one diverges. That's what we're looking at. Alright, so you should hopefully be able to start kind of seeing and expecting the result here. So this dominant term is n. This dominant term here is n squared, but the cube root, so it's really n to the 2/3 power. So n over n to the 2/3, a little bit of quick math, is going to leave you with an n to the 1/3 in the denominator. We know that n to the 1/3 is a p-series that should be divergent. So this thing right here, excuse me, should be a divergent series, but we do need to go through the process to check it. So a sub n is that one, so we're going to let b sub n. Now the coefficients don't really matter. In this case, there's no coefficients here anyway. It's 1. But I've already kind of walked through it. It would be n over n to the 2/3, but that's really going to simplify to 1 over n to the 1/3. Now I did go through a bit of mental math there and didn't write all that stuff down. Now, do I really have to go through all this? Not necessarily, because if you think about it, what could we have done up front? We haven't been doing. We could have just taken the limit of this thing as n approaches infinity. Well, the numerator grows faster than the denominator. This limit is going to go to infinity, so I really don't even need to do this. I can just take the limit of a sub n as n approaches infinity. And since I know that this numerator grows faster than the denominator, that's going to give us infinity. Automatically, since that is not 0, it's divergent. Nth term test. Probably save some time doing that instead of doing the whole ratio. Whoops. Actually did not mean to do that. Here we go. This one we will have to do a little work on. So the dominant terms are 3 to the n over 5 to the n. Well, that looks to be like it's a 3/5 to the n. That is a geometric type series. So we should be able to compare this to a geometric series and get that it's convergent, because 3/5 to the n would be r less than 1, which is convergent. So we're going to write b sub n is going to be the sum of 3/5 to the n, and we know this is r is 3/5 less than 1, therefore b sub n is convergent. So now let's take the limit. Limit as n approaches infinity of 3 to the n plus 6 over 5 to the n plus 1 times the reciprocal of this one, which will be 5 to the n over 3 to the n. Alright, these bases are not the same. The powers are the same, but the bases are not the same. The same idea should still work here, though. If I multiply two things where the power is the same, so off to the side here I'm just going to write, if I had 3 to the n times 5 to the n, that really becomes 3 times 5 all to the n power. So you can actually multiply the bases together even though they're not the same. We're not adding the exponents. The exponent just becomes distributed to each one of these. Hopefully that is something that you guys remember from algebra. So what we're going to get is the limit as n approaches infinity of 15 to the n plus, now these you cannot combine, it's just going to be 6 times 5 to the n, and then this is going to also be 15 to the n plus 3 to the n. Alright, this whole thing goes off to infinity, this whole thing goes off to infinity. We could certainly use L'Hopital's rule here and try and figure this thing out. It's a little bit more messy. What you probably want to do here is you want to divide everything, and this goes back way back to Calc 1 stuff. You want to divide everything by the dominant term in the denominator, which is the 15 to the n. That's by far bigger than 3 to the n. So what you get is the limit as n approaches infinity of 15 to the n divided by 15 to the n plus 6 times 5 to the n divided by 15 to the n over 15 to the n divided by 15 to the n plus 3 to the n divided by 15 to the n. And then we'll simplify. Limit as n approaches infinity. 15 to the n over 15 to the n is 1. 5 to the n over 15 to the n simplifies to 1/3 to the n, or 1 over 3 to the n, so this becomes 6 over 3 to the n power, multiplying the 6 up there. 15 to the n over 15 to the n is 1. 3 to the n over 15 to the n becomes 1 over 5 to the n. Now if I take the limit, this piece right here, this little piece, this little fraction right here, 6 over 3 to the n, goes to 0. This piece right here also goes to 0. So my limit is going to be 1 over 1, or 1. So therefore, since I got a finite value, I already knew b sub n was convergent. A sub n, my n's do not look good today, is also convergent. Alright, almost done, we're getting there. Okay, wanted to throw this one on there because you haven't seen anything where you've got denominators like this being added together. What we have is the dominant term in the denominator is a square root of n. Dominant term here is square root of n. So you can't add those two. I mean, you can add them together. Technically, you'd get 2 square roots of n from that. but the dominant term in the denominator is a square root of n. So if we let this be a sub n, our b sub n that we're going to compare this to is going to simply be 1 over the square root of n, which is 1 over n to the 1/2, as n goes from 1 to infinity. This is a p-series, where p is 1/2, which is less than 1, and therefore this one is divergent. So when we take the limit as n goes to infinity of 1 over square root of n plus 1 plus square root of n plus 2 times the reciprocal of this, which is really the square root of n over 1, what you get is a square root of n over the square root of n plus the square root of n as your dominant terms. Again, these plus 1 plus 2 is not part of the dominant term. So what we really get here is the same power on the top and the bottom. They're both being raised to the 1/2, so we add the leading coefficients. The difference is the leading coefficient up here is 1, and like I said before, technically this is a square root of n plus a square root of n, so it's really 2 square roots of n, so the leading coefficient there would actually be a 2, because I have 2 of these down there being added together. Ultimately, it doesn't really matter in the end if you ended up with a 1 over 1. Either way, 1/2 or 1 is going to still be a finite value, which is what we were looking for. And since we did get a finite value, we can then say a sub n is also, oops, it's divergent, not convergent. Ugly. Let's erase that. Is divergent. There we go. All right, one more to go. Okay, really, this is the same concept. You just have to be careful because it's not always that the dominant term is written first. It usually is, but in this case, the end of the fifth up here is really the dominant term. But remember, it's a square root of that. So our dominant term on the top for our b sub n is going to be an n to the 5/2. The dominant term in the bottom is this n to the 8th right here, but it's the cube root of that, so it's n to the 8/3. And then we're going to have to simplify this, so let's see. N to the 5/2 over n to the 8/3 is the same thing. We're going to have to change these to 6th. So it'll be n to the, let's see, multiplying by 3 is going to be 15/6 over n to the, multiplying by 2 is 16/6. Subtracting these two things is going to give us an n to the 1/6 in the denominator. 1 over n to the 1/6. Yeah. There we go. And this, of course, is a p-series. P is 1/6 less than 1. Therefore, b sub n is divergent. So we'll take the limit as n approaches infinity. We're going to take the limit of the division of these two things, which is going to be square root of n plus n to the 5th over cube root of n to the 8th plus n to the 6th plus 1 times the reciprocal of this one, which is going to be n to the 1/6 over 1. So what we get here is this is going to be the dominant term here is going to be n to the 5/6 limit as n approaches infinity of n to the 5/6. The dominant term here is n to the 8/3. That's not right. This is not n to the 5/6, because this is the 5/2 power, right? So we multiply, so we're going to have to add 5/2 and 1/6. Let's see, 5/2 and 1/6. 5/2 is going to be the same thing and sixth as 15/6. If I'm not mistaken. Yeah, n to the 15/6 plus, I'm sorry, times n to the 1/6. Yeah, there we go. So what we get is the limit as n approaches infinity. This, you add the two exponents together, that's 16/6, n to the 16/6 over n to the 8/3. 8/3 is the same as 16/6, so the powers are the same, so we get 1. Therefore, since we get a finite value, a sub n is divergent. All right, there you go. There you have it. There have the two comparison tests, the limit and the direct comparison test.